Okay, welcome everyone. Thank you so much for joining us today. We are having a lecture on the quantum threat to cryptography with Thomas Attema. Thank you so much, Thomas, for joining us today. Let me introduce Thomas Attema a bit. He is a senior researcher in the Applied Cryptography and Quantum Application Department of TNO and the Cryptology Group of CWI. In 2023, he obtained his PhD at Leiden University. He focuses on the development of new cryptographic techniques capable of withstanding quantum attacks and allowing data to be analyzed in a privacy-preserving manner. Thank you so much, Thomas, for being here today, and I pass you the word to start this wonderful lecture.
Thank you for the introduction. Let me start with sharing my screen. Yes.
Yes, we can see it. Thank you.
Very good. Okay, so today I will be giving a lecture on post-quantum cryptography. What does it mean? I will start with a short introduction on cryptography in general, and then I will dive into the threat of quantum computers to cryptography, and thereby also introduce the necessity and explain the necessity of migrating towards new cryptographic primitives, so-called post-quantum cryptography. So the agenda for today will, as I mentioned, to be starting with, I will be starting with an introduction to cryptography. Then I will dive into designing cryptographic primitives. So how do you actually design cryptography so that attackers cannot break it and you can preserve the privacy, confidentiality of your data? Then a very short introduction of quantum computing and its impacts to cryptography, which will be the bridge towards post-quantum cryptography, a specific sub-branch of cryptography capable of withstanding these quantum attacks. And then finally, I will talk a little bit about various ongoing efforts of migrating towards post-quantum cryptography. So cryptography, traditionally cryptography basically dealt with the following situation. You have Alice and Bob in blue and in green. They want to communicate together and they want to send each other private messages in such a way that an eavesdropper, Eve, cannot intercept these messages and read them. So basically, we want to protect the privacy or the confidentiality of this communication channel. However, cryptography entails a little bit more than only protecting confidentiality of communication channels. It also deals with protecting, for instance, the integrity. So how can we make sure that a message that Alice sends to Bob is not altered, modified by a malicious eavesdropper? For instance, if Alice wants to transfer a certain amount of money to someone else, and Bob represents the bank in this scenario, of course, we do not want the opportunity or the possibility of an eavesdropper changing or modifying that amount of money that is being transferred. So in many situations, integrity may even be more important than confidentiality of the information. Additionally, cryptography deals with the authenticity of data or information. So if a message is sent by Alice, how can Bob know for sure that this message was actually sent by Alice and not by Eve? So authenticity is also a very important cryptographic property, or a property that can be achieved through cryptographic primitives. And another one, which is a little bit less common, is non-repudiation, which basically means that if Alice sends a message to Bob, how can we make sure that Alice cannot deny having sent this message? So this is a property that's very important in, for instance, blockchain technology. So in general, cryptography basically deals with achieving these four different functionalities. Well, as probably all of you already know, cryptography is omnipresent in our current digital society. If you send a message via WhatsApp, if you visit a website or most of the websites, if you look at your medical records, if you look at payment systems, all of these systems crucially rely on cryptography. Without cryptography, they cannot function as needed. So cryptography is nowadays omnipresent in our society. So let's go back a little bit and look at a little bit of history of cryptography. So cryptography you can see as sort of an arms race between, on the one hand, code makers, the cryptographers trying to make codes, trying to design new protocols for protecting information. And on the other hand, we have the attackers, the code breakers, trying to intercept messages, trying to break the cryptography and break these properties. And this goes back a very long time. So I think the first examples of cryptography can be found in the hieroglyphs. So not traditional hieroglyphs. They cannot, or they should not be considered as cryptography. But if you look at certain hieroglyphs, what you saw is that the makers of these hieroglyphs, they sort of made changes to protect or to hide the actual message. So they used non-standard hieroglyphs, and the idea was not really to hide the information, but to create a puzzle, like for the bystanders or the people passing by. So this can be seen as sort of some of the first occasions or implementations of cryptography. People trying to modify the hieroglyphs to protect or to hide information beneath it. Well, nowadays we know how to solve these hieroglyphs, or actually back then already certain bystanders were able to solve these puzzles, and they basically broke the cryptography, if you will. Then if we move on a little bit, so we have Caesar cipher dating back from the time of Julius Caesar. Julius Caesar actually used cryptography to communicate with his generals in the field. So of course there it was also very crucial that the information that Julius Caesar sent to his generals was not intercepted, was not seen by the adversary, by the enemy. So therefore he used a very simple code, cipher, basically rotating the alphabet by a few letters, and thereby creating, hiding the underlying information, the underlying data. So this is one, very simple example of cryptography. Maybe some of you have played with this Caesar cipher already when you were kids. But this is a very nice way to get introduced to cryptography. Nowadays, of course, we know that this cipher is far from secure, and we have a lot of very efficient techniques for breaking this cipher. But it took some time to develop the theory to actually break the Caesar cipher, as you can see in this timeline. So then we jump ahead a little bit. So this is another example of cryptography, the Vignere cipher. And this Vignere cipher was actually called Le Chiffre Indéchiffrable, which translates to the unbreakable cipher. So back then, people thought, well, this cipher, this piece of cryptography is so complicated, we will never be able to break it. But of course, those people turned out to be wrong, and it took about 300 years and for someone to find a solution to this cipher and to actually break the cryptography. So nowadays we cannot use this Vignere cipher anymore because we have a solution for breaking it. So you see this arms race going back and forth. A new cipher is being introduced, and then it takes some time for the attackers, the code breakers, to actually break this cipher. Well, then we jump ahead again. Many of you will probably be familiar with the Enigma code, a cipher used by the Germans in the Second World War. There are various interesting books and even movies about the Enigma code and its importance in the Second World War, and also the efforts by Alan Turing and some others in actually breaking this Enigma code, and how the breaking of the Enigma code actually altered the course of the Second World War. So also this code was used heavily and with very crucial applications, of course, in the Second World War. But Alan Turing and others, they found a way to actually break it. So nowadays we can no longer use the Enigma code because we know how to break it. So again, an example in this arms race. So then we jump ahead again to the present time, basically. So what we're doing nowadays, we're nowadays using also various cryptographic techniques, cryptographic protocols to protect our information. And one very prominent one, an example, is the RSA encryption scheme, or the RSA digital signature schemes. This cryptographic primitive was introduced in 1978, and we still use it today. However, we know that this cryptographic primitive can also be broken, but only if we have a quantum computer, a quantum algorithm. So already in 1994, Peter Shor devised a quantum algorithm. So that's a specific kind of algorithm that you can only run if you have a quantum computer to break the RSA encryption scheme. So that was a very interesting result. But back then, we didn't worry too much about this cryptanalytic, this attack. And the reason was you need this quantum computer, and back then there was no quantum computer capable of running a Shor's algorithm. So this is only a theoretical vulnerability back then. However, nowadays we basically see that the maturity of quantum computers is increasing, and this threat is becoming more and more serious. So that's why the last decade, basically, we've started to take this quantum threat more and more serious as well, and we've looked for other means of performing cryptography techniques that are capable of withstanding quantum computers, quantum attacks. So in short, when we will have such a quantum computer, a so-called cryptographically relevant quantum computer capable of running Shor's algorithm, so it should be large enough, it should have enough qubits. We will dive into all of these properties a little bit later on today. But once we have one, we know that many of the cryptography that we're using nowadays, for instance, the RSA, but also some other schemes, will be broken. The point is, however, we don't really know when this will happen. This can be in 2030, it can also be 2050, and it can also take even longer than that. So we are very uncertain when this will happen. So we're in this strange stage where we have theoretical attacks, but no practical means of executing these attacks. But again, a key point or a key message here is that you could just see this post-quantum cryptography as the next chapter in this arms race between code makers and code breakers, where in this new chapter, code breakers will have quantum computers to their disposal. But also a very quick history of cryptography. Now, if we dive into the field of cryptography a little bit more, a little bit deeper, then we observe that there are basically two important categories of cryptographic primitives. The first one is symmetric key cryptography. And the property of symmetric key cryptography is basically that you require the same key to encrypt as you do to decrypt. So both Alice and Bob, if you remember the first picture I showed you, require the same cryptographic key to encrypt and decrypt. That's why this is called symmetric. And many of the schemes that we saw in this historical overview are actually symmetric key encryption schemes. So the Caesar cipher, the Vignera cipher, the Enigma codes, but also AES, the DES, and some other examples. These are all symmetric key cryptography. And one of the properties is that symmetric key cryptography is very efficient. However, an important downside or a crucial drawback of symmetric key cryptography is that you still need to distribute this secret key over the parties that want to communicate. Which basically means that if you want to communicate a private message to someone that you've never met before, this is going to be problematic, because how can you make sure that you have the same secret key to protect your message if you haven't ever met this person before? So For military applications, for instance, symmetric key cryptography often suffices, not always, but often. But if you want to communicate on the internet, symmetric key cryptography is rather limited. So fortunately, nowadays, we also have asymmetric cryptography or public key cryptography. And this is a very nice notion, a nice concept that was introduced in the 1970s. So RSA is one of the first examples of such a public key cryptography, cryptographic scheme. And what it basically does, it uses two different cryptographic keys. One public key, the yellow one in this picture, to encrypt information, and another one, a private key, to decrypt information. And the nice thing about this scheme is that this public key, anyone may know the public key. So you can share the public key with everyone on the internet. This does not have to be a secret, but the private key, of course, has to remain a secret. So you just keep the private key hidden from everyone else in the world, and you share this public key with everyone that you would like to be able to communicate with you. So this is, of course, very convenient property because that allows you to also communicate with people that you've never met over the internet, for instance. However, a downside is that asymmetric key cryptography is in general a little bit less efficient than symmetric cryptography. So that's why we typically use it in combination. We basically combine the best of both worlds, the efficiency of symmetric encryption, and then we use the asymmetric encryption to solve this problem of distributing the secret keys. So RSA is one of the examples that I mentioned already before of public key cryptography or asymmetric cryptography. Elliptic curve Diffie-Hellman, elliptic curve digital signature schemes. These are all examples of public key cryptography. And what is important to note is that the security is actually is always based on the hardness of certain mathematical problems. That's something I will come back to in the next few slides. So the impact of quantum computing on cryptography is the largest, is the biggest for this second category of asymmetric cryptography. So that's also why we will be focusing on this second category today. So designing cryptographic primitives. So let's see if we want to develop a cryptographic primitives. Let's for simplicity focus on encryption. So we want to hide information from a malicious adversary or an eavesdropper. What we want is we want to have certain encryption functionalities. So encrypting, we want to be able to transform data, private information, into a ciphertext by this encryption procedure. And this should, of course, be efficient. It's not practical. It doesn't work if encryption takes you a very long time. So this should be an efficient procedure to encrypt your information. But on the other hand, if you want to decrypt your information, so if you obtain a ciphertext, then you should also be able to decrypt efficiently, but only if you have access to the private key. So you have this private key, and if you have access to the private key, then you should be able to efficiently decrypt your information. Otherwise, of course, the ciphertext will be useless. So this is Bob trying to retrieve the confidential or the private information from the ciphertext. However, decryption without the private key, that should be extremely hard, because this is exactly what an adversary, what an attacker tries to do. It tries to obtain this sensitive information without having access to the private key. So this should be extremely hard. So if you look at these properties, what we actually want in mathematical terms is a one-way function. So we want a function such that going from A to B is easy, is efficient, but going from B to A is hard. So what this actually means is you can look at this as going from A to B you can see that as encrypting information, but going from B to A is decrypting information. And if you don't have this private key, you should have this property. And this is exactly what a one-way function does. So one-way function is easy in one way, but very hard the other way. So on a very high level, if we find these one-way functions, if we have an example of such a one-way function, then we can typically use it to build cryptography. We can, if we have the right properties, we can use it to build these encryption schemes, for instance. Let us look at an example. So this is actually the example that was used by the RSA encryption scheme, and that's namely factorization. So the first observation is that multiplying two numbers is easy. We can efficiently perform these multiplications. So of course, if the numbers become bigger and bigger, it requires a little bit of more power or efforts to perform these calculations. But all of us know how to perform these calculations. We do not even need a calculator to do these multiplications. So this is an efficient procedure. So of course, the numbers that we are using in cryptography are much bigger, and therefore we do use computers and calculators basically to perform these multiplications. But still, the point is that multiplying two numbers is an easy operation. We know how to do it efficiently. However, if you go the other way, if you try to go the other way around, so if I give you a number, I give you 57, and I ask you to factor it to find the two factors that multiply together to 57. This is a rather difficult operation, actually. So probably if I try you to solve this puzzle, you will try you will try several options until you find actually the factors. So this trial and error is basically the best way we know of finding the factors. And this, of course, is quite a cumbersome, complicated procedure. So we don't have an efficient procedure to find the factors of numbers. Well, for 57, you can still do this trial and error, and you will find the factor. This number 4171 is already a bit bigger, so this trial and error, yeah, you probably don't want to do it by hand, but if you really want to, you could probably. Well, and if we keep increasing these numbers, well, this just becomes an infeasible problem, and it becomes, even for the largest supercomputers, it becomes impossible to perform these factorization, to solve the factorization problem. So this basically shows that factorization or multiplication is sort of an example of a one-way function. So multiplying two numbers going from A to B isn't easy, but going from B to A, factoring these numbers is a difficult problem. And there were some very smart people, Rives, the Shamir, and Adelman, the people depicted in this figure. And they designed the RSA encryption scheme actually using this hardness of the integer factorization problem in 1978. And by that, they devised an encryption scheme and also a digital signature scheme. What is further also good to be aware of, that mostly we actually do not know how to prove security. So we don't have any mathematical guarantees that the RSA encryption scheme, for instance, is secure. But security is only assumed to hold. So we're assuming that this problem is actually hard and that we cannot factor it. So this feels rather weak, rather shaky. But for this reason, it's actually very important to perform cryptanalysis, so to try to break these underlying assumptions. And what cryptanalysis basically does, so they try to break the assumption, break cryptographic primitives, and either they succeed and they can invalidate assumptions, so we can discard, throw away the insecure schemes. And they can also help in quantifying the hardness. And if for many years people have tried to break a cryptographic scheme, so for instance, people have tried to break the RSA encryption scheme already since 1978, or since it was introduced, and people kept failing at this. So nowadays we have we're quite confident in the security of the RSA encryption scheme, simply because so many people have tried to break it and they were all unsuccessful. So in cryptography, it actually takes many years of cryptanalysis, of analyzing these protocols before we actually trust the protocol to be secure. So this is not only for the RSA encryption scheme, but for any cryptographic primitive that is introduced. Yes, and decrypt analysis is yeah, you could see that as part of this arms race between code makers and code breakers. Okay, so now let's bring quantum computing to the equation. So quantum computers, what are quantum computers? Quantum computers are they work fundamentally different than classical computers, and we will not dive into the details of quantum computing, but I will mention that instead of using bits, quantum computers make use of so-called qubits. So a bit is either a 0 or a 1, so you basically have two options, and then you can encode information in bits. That's basically what computers do, and they perform operations on these bits. And if you tie that all of that together, you can do amazing things that we now yeah, do with our classical computers. So quantum computers on the fundamental level, they work with qubits, can actually be these linear combinations of a 0 and a 1. So instead of taking these two positions, 0 and a 1, a qubit can take any position basically on this sphere. This is a so-called Bloch sphere. So in some sense, a qubit is a combination of a 0 and a 1. And if you use that in the right way, quantum computers do, they work with many qubits, they try to work with many qubits, and they perform operations on these qubits. This is all quite challenging and complicated, but if you manage to do that, then you will derive at a very different computational model, and you can do, well, you can perform certain algorithms and solve certain problems that are infeasible for classical computers. And as an important example, so this factorization problem that we mentioned before, it's very hard for classical computers to solve it, but we know that quantum computers can solve it efficiently. So there's a big difference there between classical and quantum computers. So this picture actually shows an example of a quantum computer. There's a lot of interesting and complicated physics going on in there. What must be mentioned though is that it is very difficult to build a quantum computer. So the qubits, it's very difficult to make sure that these qubits are stable, so they don't decohere into something else, that we have error correction on the qubits. All of these things are very difficult to achieve. And this is where a lot of the research or academic efforts have gone into the last decade. And some amazing progress has been made, but still the current quantum computers, state of the art in quantum computing is rather limited in what it can achieve. So we're at this phase where quantum computers are improving, getting better and better, but they're still not able of breaking our RSA, for instance. And the final bullet here basically reads that quantum computing, so they introduce a new computational paradigm, which also means that it redefines which computational problems are hard or are difficult to solve. And this is exactly what is essential or crucial in cryptography, that certain computational problems are hard. So the impact of quantum computers on cryptography is actually significant. Further, what is also good to mention is that a quantum computer is not just a very fast supercomputer. It really works fundamentally different. And so it's also not the case that any problem that a classical computer can solve can be solved more efficiently on a quantum computer. For many problems, a quantum computer is not the way to go. Does not give you any improvement over a classical computer. So that's also important to realize. But for very specific problems where there is a certain underlying mathematical structure, quantum computers can significantly outperform classical computers. So Shor's algorithm, I already mentioned this before, so it was introduced in 1994. So even before we had any quantum computing hardware, we just had the concept, the theoretical concept of a quantum computer back then. And still, Peter Shor devised this algorithm, so that's quite impressive. And basically, this algorithm provides an exponential speed up in solving this factorization problem that was used for the RSA encryption scheme, and also for solving the discrete logarithm problem. I've not introduced this problem, but it's something similar. Then in 1996, another famous quantum algorithm was introduced. It's Grover's search algorithm, and it allows you to search through unstructured databases. And this allows you to speed up certain brute force searches quadratically. And this can be used if you want to do a key search. So this can also be used in certain quantum attacks of cryptographic primitives. However, the impact here, the speed up is only quadratic and not exponential. And also there are some other constraints and caveats in performing Grover searches. So the impact of Shor's algorithm is much, much bigger than the impact of Grover's algorithm for now. So if you translate this to symmetric encryption and also asymmetric encryption, we see that the schemes mentioned here, the asymmetric cryptography that we've been using a lot, RSA elliptic curve cryptography, that's actually completely broken by quantum attacks by using Shor's algorithm. And these symmetric ciphers that we've been using, like AES, for instance, that's actually slightly weakened by quantum attacks by running Grover's algorithm. So this is the effect on symmetric key cryptography is less severe than on asymmetric key cryptography. And if we dive into that a little bit more, then we see that what I mentioned before is theoretically Grover can speed up the attacks on symmetric key cryptography. At face value, if you just look at this theoretical results, then you should increase the size of your keys. So for instance, you should instead of using AES 128-bit, you should use AES 256. So this number basically defines the complexity of your encryption scheme, so the length of your key. However, if you do a more detailed analysis of Grover attacks, then you can see or identify that they are a very long way from feasible. So you need a vast amount of quantum resources, and also Grover attacks are not parallelizable. So in fact, many organizations they do not shy away from advising the use of AES 128. So AES 128 is likely to remain secure for a very long time. So do not worry too much about the threat of quantum computing to symmetric key cryptography. That's basically the main message here. That being said, we still advise the use of AES 256 where possible, just to be on the safe side, just to be conservative. But definitely do not prioritize the migration of AES 128 or the migration of symmetric key cryptography in general. So that provides a little bit of a nuance. Now let's go a little bit back to the state of the art of quantum computing. I already mentioned before when Grover devised his came up with his algorithm in 1994. We didn't have any quantum computers at all. So nowadays we see billions of investments going into quantum computing. So a lot of organizations, governments, institutes are focusing strongly on quantum computing because of all the potential benefits that you can derive from them. And we've been seeing many different breakthroughs in the field of quantum computing. So this is the first news article is already a little bit outdated, I guess, 2019. But then we saw that Google published the results where they claimed quantum supremacy. They basically claimed to solve a problem on their quantum computer that was infeasible of being solved on the classical supercomputers. So this result was later on a little bit disputed because some others they came up with results of actually performing the same analysis on classical computers as well, more efficiently than what was claimed in this original Google paper. And also the actual application was sort of a random problem. It was not a useful problem that they were solving. So that more recently, in 2023, IBM claimed that the utility of quantum computers is near. So we're getting closer to actually seeing useful quantum computers. Last December, So a few months ago, Google announced their new chip, the Willow chip, which is actually able of doing a certain error correction in the field of quantum computing. And even more recently, so last month in February, we saw some new results by Microsoft, them revealing their new quantum chip. So we see many breakthroughs actually in the news. It's a little bit hyped, but you do see that there is development and many investments in the field of quantum computing. However, you can definitely nuance these claims a little bit. So these are also very recent news articles, all from this year, so January and then also February, where actually the same organization. So here, for instance, we see Google CEO still explaining or nuancing these claims that practical quantum computers are still likely a decade away. The CEO of NVIDIA, Jensen Huang, he actually explained or he predicted useful quantum computers to be approximately 20 years away. This caused a huge shock on the stock market of quantum computers. So it's very hard to judge. We're sort of in this high bubble where we see many different breakthroughs and huge investments going into the field of quantum computing. So there's definitely something of a potential, but at the same time, it may still take quite some time before quantum computers actually become useful. And if we try to plot these results a little bit, so again, this is just a figure of where we plot the number of qubits of these different machines. So that's actually only one figure of merit. There's many more figures of merit that you should look at. So do not only look at this this graph. There's more information to take into account whether you want to when you want to judge the usefulness of quantum computers. But if you look at all of this, you do see a clear trend that many different quantum computers, so every color represents a different manufacturer, a different company building quantum computers. You see that they are slowly making progress and increasing the sizes and capabilities of their quantum computers. So it's difficult to judge all of these developments, but we are seeing some progress in the field of quantum computers. So this is definitely not something to ignore. So again, it will probably take many years before quantum computers will be able to break cryptography, so become relevant for cryptographic purposes. However, there's some other things that we have to take into account. For instance, the history has shown us that migrating to new cryptography, so to replace vulnerable cryptography by stronger cryptography, is a very complicated task and takes time. So previous examples are DES and MD5. And these were cryptographic primitives deployed broadly, but later turned out to be insecure. So replacing them, that took easily took decades, or a decade to do that. So migration of cryptography is a very complicated task. So you need to start early with this task. Further, encrypted data that is transmitted right now can be eavesdropped and decrypted later. So what an adversary may do is it may intercept all of these messages that are encrypted now and secure now, and just store them and wait until they have a quantum breaking them. That sounds a little bit far-fetched, but it actually isn't too far-fetched. So we know, for instance, that the NSA is storing a lot of data, keeping track of a lot of data. So they may very well be executing this strategy for certain highly valuable information. So taking this into account, you have to think about how long your data should be secured. So if you take these aspects into account, Mosca, as a scientist, he actually came up with this very simple theorem that basically says, well, you have to compare X, the time it requires to update your IT infrastructure, so the migration time, and the time you want your information to be protected, Y. And you want X plus Y to be smaller than Z, which is the time it requires to develop a quantum computer. So taking into account that X may be a decade, for instance, maybe 10 years to replace to update your IT infrastructure. And also for some information that you're sending right now, it may still be valuable, sensitive information 10 years from now. Sometimes some information we already know right now that even 50 years from now, this is still going to be sensitive information. Think about your medical records or state secrets, for instance. We don't want our state secrets from 10 years or 50 years ago to be revealed all of a sudden. So these numbers can be quite large, and that basically means that for some situations, some scenarios, we may already be too late with migrating to post-quantum cryptography. So Moscow's theorem actually states that you should be this graph should look a little bit different. Z should actually be larger than X plus Y. Then you're on the safe side. And in this example, we're actually already too late with migrating or updating our IT infrastructure. So in cryptography, the summary here is in cryptography you have to take future threats into account, and you have to look quite far into the future to remain secure. Okay. So then this is basically the sort now decrypt later attack that provides the urgency, or that shows the urgency of taking this quantum threat into account. And the urgency mainly applies to the confidentiality of data for integrity, authenticity, and also non-repudiation. Well, maybe the store now decrypt later attack is a little bit less relevant. But for confidentiality, you should really take that into account. Well, fortunately, there's various ongoing efforts already to migrate to post-quantum cryptography. So, for instance, in May 2022, the US White House, they set out or they published this memorandum, and it basically directs all government agencies to take action to mitigate this quantum threat. So already in the US, we've from 2022, we've already seen these legislation, basically, this guidelines policy in place of mitigating the quantum threat. Also, a little bit more recently in the US, the CNSA 2.0 was published, and this basically mandates all US national security systems to migrate to PQC. So these are also critical systems like the energy sector in the US that make use of that are being protected via cryptography. So they should start migrating already. And for some applications, they should already have migrated in 2030 or 2033. So that's already quite soon. So we see that this migration to post-quantum cryptography has already started. Okay, I think I have to speed up a little bit. So what is post-quantum cryptography? So post-quantum cryptography is basically cryptography that is secure against quantum attackers. So even an attacker with a quantum computer, with such a powerful quantum computer, will not be able to break this cryptography. And what we actually need to do is we need to base our cryptography on different mathematical problems. So the first part of the presentation where I talked about designing cryptographic primitives, that still holds. We still need to find these hard mathematical problems, these one-way functions. However, we have to base them on different mathematical problems. So multiplication and factorization no longer works because this problem becomes easy for quantum computers. But we need to find other mathematical problems. So fortunately, there are quite a few different mathematical platforms that can be used to build cryptography. These are just a few of them. Some of them we've known for quite some time already, but we never really investigated or dove into deploying these kind of cryptographic primitives because they are way less, or they are less efficient than RSA or elliptic curve cryptography. But now we really have an urgency to start deploying them.
Sorry
yes.
for interrupting, Thomas. There are 5 minutes left just until the Q&A, and just to let you know. Thank you.
Yeah, thank you very much. Then I will speed up a little bit. So So this is also important. So NIST, the US National Institute for Standards and Technology, they started a competition already in 2016 to come up with new cryptographic standards, post-quantum cryptographic standards. So this is a very detailed, cumbersome process basically to come up with new cryptographic primitives to make sure that the entire world can analyze them and that vulnerabilities are being discovered and everything. To come up with these new standards. So 8 years after the start in 2016, in 2024 namely, so very recently, the first set of standards were published. So now we have these three cryptographic standards that are secure against quantum computers. So they can be deployed already. And this week, actually, a new key encapsulation mechanism was selected. So based on a different mathematical platform to ensure diversity. So the details are not too important here, but basically after a very long, thorough process, the cryptographic community came up with new cryptographic standards that should be able to withstand quantum attacks. And this is all very recent work. And nowadays, the deployment and the migration towards these new standards has started. Well, the fact that this took 8 years already shows that standardization is not a straightforward process. There are some examples of vulnerabilities being discovered in a very late stage of the standardization. So some psych, for instance, was a very promising candidate, but still it was broken 6 years after the start of the NIST procedure. So that was quite a shocking event. And also implementing cryptographic primitives is not too easy. So some of these, so Kyber is one of the winners of this competition, basically. And Kyber Slash is a side channel attack, an attack on the implementation of that primitive. So theoretically, it is secure. However, if you implement it in a faulty manner, which was done here, then you can still introduce vulnerabilities. So standardization and also implementation of cryptography is going to take some time, and this is also a difficult process. So let me very quickly go through these slides. So migrating to post-quantum cryptography basically means that we will take out current cryptography that's vulnerable to quantum attackers and plug in this new post-quantum cryptography. So this is also going to be a challenging task, basically because cryptography is omnipresent. So we're using cryptography in many, many different places. So it will take a long time for us to find out where we're using cryptography and also to replace it. So the last couple of years, people have worked on sort of formalisms, techniques, or guidelines on how to start this process of migrating to post-quantum cryptography. And some organizations have already started or have already migrated. So certain message protocols such as Apple's iMessage and also the Signal protocol, they've already added quantum resistant or post-quantum cryptography. This Tutanmail server uses post-quantum cryptography to protect email. So it's definitely possible already in practice to deploy cryptography, and we're seeing more and more examples. In fact, if you're using a Chrome-based browser, then since last year, the TLS 1.3 by default selects the post-quantum cryptography, namely this Kyber algorithm. So that's also a nice development. And here we see some graph where we see a peak in the usage of post-quantum cryptography by users of the Cloudflare content delivery network. So basically, in summary, it's important to migrate to post-quantum cryptography. It's going to be a challenging task, but it's definitely not impossible. And we're seeing more and more examples of organizations that have already started or even completed this migration. So it's definitely possible to do this the coming years. So thank you, and I'm happy to
Thank
dive into
you.
some of the questions.
Thank you so much, Thomas. What a very interesting lecture. Again, I knew nothing about it, so thank you so much. And I'm sure everyone, in fact, I already see is raising their hands to ask questions. The first one is Thuso. I will allow your mic. Please unmute yourself. Thank you.
How are you? Can you hear me?
Hello. Yes, we can hear you. Thank you.
Yes.
Okay. Good day, everyone. Today, I just want to know, is quantum AI computing assisting in the safety or the security, actually, of cryptographic keys on the internet? Because nowadays, malicious actors can compromise other users' public keys, for making them unable to access their own accounts. So that's the only question. Is there AI computing, AI computing assisting towards this issue? That's only my question.
I'm sorry, it's a little bit hard to follow the question. So there's some noise.
So why don't you try dropping the question in the Q&A chat so that maybe we can read it out, just because it was hard to understand what you were saying. Moving on, just to make sure we don't lose any minutes. Pumelelo, if you would like to unmute yourself, you can ask your question. Thank you.
Hi, good afternoon to everybody. Thanks to Thomas for a great presentation. It was very enlightening. Like it shed a lot of light about the importance of cybersecurity to me in real life, and with regards to like communication and its relationship to mathematics. I was hoping that Thomas could share recommendations of like resources one could consult as somebody with no background in IT, because when I was about to join the course, I was told that I didn't need a background to IT to understand cybersecurity. But a few of the lectures that we had earlier, people were speaking English, but it sounded like Greek to me. So I think it would help if you would give those of us with no background in IT and maybe even maths resources to consult to make learning cybersecurity easier. Thank you.
Okay, makes a lot of sense. So especially like the cryptographic primitives and the mathematics behind it, they can seem quite daunting and complicated. So it's a bit hard for me to recommend any material on cybersecurity in general. So let me stick to my area of expertise, cryptography or post-quantum cryptography. So this is one of the documents that we published actually December last year, 2024. It's a second edition already, so the earlier version stems from 2023. And this is a very high-level overview on the PQC migration it's a handbook on the PQC migration. And its intended audience are definitely not only IT experts, so also policymakers. So it should give you a high-level overview, and then if you go to the end of the book, then more and more details will surface. But especially the beginning and the introduction should definitely be readable. So that's something that I can recommend right now, and also it contains a lot of references to other material. So and another source of information could be the US National Center of Excellence for Cryptography. So that's also part of NIST. They also have a lot of reference documents on cryptography that should be quite accessible. ETSI, so the European Standardization Organization, they also have quite a few white papers that do not dive too much into detail. So hopefully this gives you a good starting point.
Thank you very much.
Okay, moving on. Thank you, Pumelelo, for your question. Chanda, you are unmuted. You can ask your question. Thank you. Perhaps Chanda, if you can unmute yourself as well, because we can't hear you.
Thank you very much, Thomas, for a great presentation. My question is, how may geopolitical tensions, e.g. USA-China tech rivalry, fragment NIST-driven PQC standardization efforts? And may you propose mechanisms for harmonizing EU, ISO, and BRICS post-quantum policies without compromising cryptography integrity?
So again, this was somewhat difficult for me to understand, but were you referring to the fact that standardization is mainly a US effort, or and how we can protect against backdoors or vulnerabilities being introduced there, or?
I'm saying that how may geopolitical tensions, e.g. USA-China tension and rivalry, fragment the NIST-driven PQC standardization efforts? And may you propose mechanisms for harmonizing EU, ISO, and BRICS post-quantum policies without compromising cryptographical integrity?
So I think I can say a little bit. I did not fully understand the question, but I can say a little bit about the standardization efforts in the US and what their intention is. So what I think is good to realize is the fact that, of course, this standardization effort was led by a US agency, NIST. However, they from the start they intended to make this process as open and international as possible. So we see that the submissions to the competition were by people from all over the world. So we saw submissions from every part of the world, basically. So it was a very international effort. It was an open process. And in fact, NIST tried to have like a European or another country pick up this task and lead the standardization effort, just to make sure that the people did not feel like the standards are just US standards. So I think you should view the standards as really an international global initiative and not really a US initiative. So hopefully that sort of answers your question, but I'm afraid I did not fully catch it.
Yes, perhaps also if there are any questions, if you have background noise, it's always best to write the questions out in the Q&A box just to make it easier for our lecturers to understand. But thank you for asking the question, and just thank you, Thomas. We've got about a minute left, and since we do have a class after, I would wrap it up here if that's okay with you. Again, thank you so much for being here and for giving us a very enlightening lecture. And yes, I see everyone's also applauding and thanking you. It was very, very well received. And I hope you have a great day. And for everyone else, we have a lecture on the ethics of AI in 15 minutes. Thank you again, Thomas.
You're very welcome. Thank you. Bye-bye.